The second new concept that we have to deal with in dealing with fluids is density. Mass is not a very good concept for dealing with fluids in general because the fluid, again, can take the shape of the container. For instance, in a gas, one can compress a gas into a smaller volume, or one can expand it. One can open and put more gas in the same container if you compress it than you can if you had it at lower pressure, so you can change the amount of mass even though the volume of the container doesn't change. For another purpose, density is a better measure because density is what's called an intensive property. An intensive property is a property that is independent of the amount of something you have. So for instance, the density of gold at a given temperature is unique to gold. But the mass of gold is not unique because it depends on how much gold you have. So we're going to want to bring and get away things like volume and area. So we've already adjusted force in F equal ma to create pressure by dividing by the area. Now we want to take the mass on F equal ma and we want to get volume out of it by dividing by V. And when we do this, we get what's called density, or more precisely, mass density. So mass density, what we want to do is talk about mass per volume. The symbol is rho. By definition, it is mass over volume. In a calculus-based course, we would again want to take the limit over a very small volume because the thing may be in clumps or something. It may not be smooth with a constant density, but we won't worry about that here. So mass divided by density. Mass divided by volume. The density of an object is uniformly found this way. Let's look at some other things. I already said about it being an intensive property. Mass is an extensive property. It's extensive because it depends on the size and therefore is not unique to the object. We need some units for this. The units that we normally use would be the kilogram per meter cubed. However, this is extremely large. So you're going to be dealing with very large numbers if you do that. Well, it turns out density is used in lots of other places, so it tends to be a fact that more people work in grams per centimeter cubed. So 1 gram per centimeter cubed, and then you want to find out what that would be if you had that in kilograms per meter cubed. It would be 1,000 kilograms per meters cubed. The density of water is 1 gram per cubic centimeter, which means that it takes 1,000 kilograms in a meter cubed. Think about this. If you had a meter, so a little more than a yard high, 1 meter wide, like this, not a big enough swimming pool to even get in, right? Very small. There's 1,000 kilograms. That means the weight's about 2,200 pounds. Water has a tremendous amount of weight. If you get in front of a storm or a flood, if a dam breaks, if it even shoots a water hose at you, there is a lot of weight in a very small amount of water that can come in and literally smash your car, drive you into a river, and can kill you. You should appreciate the fact that water has a lot of weight. You can't stop it with just yourself. Rather than do like these, what we often will do is speak about specific density. Specific density is the density of the material divided by the density of water. So as you can see, since the density of water is 1 gram per cubic centimeter, then we'll often have something like, for instance, 8 grams per cubic centimeter divided by 1 gram per cubic centimeter is just 8. This happens to be a unitless quantity. and it's good no matter what unit system you're using. Know the specific density, multiply by the density of water in whichever system you want, and you have the density of the material that you're looking for. All right, that's all there is to this very simple concept.